So in this concept bite, I'm going to discuss reaction coordinate. And reaction coordinate is something that we've all almost certainly seen, but never really probably thought about a lot. The reason I say that we've all probably seen it before is because we see them in reaction profiles. So here is a kind of a typical, you've seen it in high school, reaction profile whereby we have our reactants and we have our products and we have some sort of activation barrier and it passes through a transition state, and we usually have some sort of energy label. I've got free energy here on your y-axis, and the x-axis, if it's labeled at all, which sometimes people don't, should be labeled with the reaction coordinate. And what this is basically showing you is how far through a reaction that we've been. So we start off on our reactants, and as we progress through the reaction towards our product, we have to pass over this transition state, which takes a increased amount of energy, and I kind of progress down into my products. But when we meet the reaction coordinate in photochemistry, we don't see them looking quite like this profile, because in photochemistry we show a profile which includes the potential wells, and it includes the wave functions usually of the different vibrational energy levels, and we label that with reaction coordinate. So what in this case do I mean by this term reaction coordinate? Now, I think it's really important to break down what's going on this image. And so here you see that I have labelled an absorption transition going from the bottom vibrational level of the ground state, exciting vertically upwards until I get into this second vibrational level of my excited state. And then I've got the emission coming from the ground vibrational level of the first electronic excited state. And we've seen this, and we've labelled this difference in energy I get between my absorption and my emission transition as my Stokes shift. And this Stokes shift is very much this idea that we have this difference in energy between my ground and my excited state structures, this reorganization energy. Surely this must come in somewhere to this reaction coordinate, because I've labelled that x-axis the reaction coordinate, and the two wells are offset on that x-axis as well as electronically because of the energy level of the excited state along the y-axis as well. And so we can think about this reaction coordinate in different ways. We can think about it as being what it fundamentally is, a kind of a net measure of the wave function of the ground state and the wave function of the excited state. But as a picture in my head, that doesn't really get me very far. And so another way to think about it is almost to do with the structure. Because the bigger the structural changes within my molecule, the bigger the difference between the wave functions will be, and therefore the bigger effect it will have on the reaction coordinates. And so if I were to look at two profiles with different offsets on the reaction coordinate, but otherwise identical differences in energy, why would I end up with these two different looking profiles? Well, I would be saying that in the profile that appears on the right of this, that I have a bigger structural difference, a bigger difference in the wave function, and therefore a bigger difference in the overlap integral, which is what those vertical arrows are measuring between my ground and my excited state. So the reaction coordinates are really quite amorphous idea, and we use it to cover quite a lot of sins in chemistry. But it's this idea that that it is a measure of a difference between our ground and our excited state. And you've got to remember that the difference between the ground and the excited state in photochemistry is just a reactant and a product. I hope this has helped. I will see you in some other videos. Bye bye.